Hello, this week we're going to cover Chapter 4, Systems of Linear Equations. Now, in our last chapter we took a look at graphing, but we can actually use graphing to help us solve systems of linear equations. Let's take a look at that. Now, when I draw a line on a graph, that line is the set of all solutions to an equation. So every point on that line is a solution to our equation. When I draw another line on that same graph, that is another set of solutions for a different equation. But the point where they meet, right at that intersection, that point is a solution to both equations. So a system of linear equations, what that means is I'm taking two equations and I'm finding a solution that works for both. So we can use graphing to help us find the solution that works for both equations. There are circumstances, however, where our lines will not cross. For example, if I have a solution to a set of equations here, and then I graph another set of solutions, if that set of solutions creates a parallel line to my original equation, this then will never intersect, which means for these two equations, they will never have a point that is a solution to both equations. So in this case, there is no solution. However, if I have another line that when I graph it exactly overlaps the previous equation, in that case, I have infinitely many solutions. An example of this would be, say I had the equations y equals x and 2y equals 2x. If I were to graph these two equations, they would both give me the exact same line. So in this case, these two would have infinitely many solutions in common with each other. Now let's take a look at this first situation where we have those two lines that meet at one point. Let's say I have the equations x plus y is equal to 10 and x minus y equals 4. What I want to do now is check to see if this one point, say 7, 3, is a solution to both equations. The way we can check that is just by plugging those numbers into both equations. Again, always x is our first number, y is our second. So we have 7 plus 3 is equal to 10, and indeed that is true. Here 7 minus 3 is equal to 4, and again that is true. So this point 7, 3 is a solution to these two equations. It is a solution to our system of equations. What about the point 4, 6? Can we check that the same way? 4 plus 6 is equal to 10, and that is true. 4 minus 6 is equal to 4. That is not true. 4 minus 6 is negative 2, and negative 2 does not equal 4. So in this case, this may be a solution to this first equation, but since it is not a solution to both equations, it is not a solution to our system of equations. So only the 7, 3 is the solution that we are looking for here. Now let's try finding a solution using graphing. Let's take the two equations y equals 2x and 2x plus y is equal to 4. Now this first equation is already written in slope-intercept form, so I can leave it like that because it'll be easy to graph. This second equation I'm going to rewrite into slope-intercept form. I'm going to subtract 2x from both sides, and so I have y is equal to negative 2x plus 4. Now I'll go ahead and graph both of these. This first equation has an intercept of 0, 0, and then I go up 2 and to the right 2 to get my next point. If I carry that on, it goes up like this. This second equation has an intercept of 0, 4, and then goes down 2 and to the right 1. each step, so it goes on and carries on in this direction. So the point right here is the solution to both equations. That point is the point 1, 2. Now let's go ahead and check this to make sure that it indeed is a solution to both equations. Plug in 2 for y and 1 for x, and 2 does equal 2 times 1. Over here, plug in 2 for y, negative 2 times 1 plus 4. So 2 is equal to negative 2 plus 4, which indeed is true. So this indeed is a solution to both equations, and we're able to find it graphically. Now the problem with finding solutions graphically is that it can be very difficult to tell exactly where those two lines cross. For example, how am I supposed to know that that is the point 1, 2 as compared to 0.99 and 2.001? I know that it is the point 1, 2 because it was proven to be a solution to both equations. But just by looking at it, I cannot be sure that it is 1, 2. So let's take a look at a more concrete method of solving systems of equations. We're going to next take a look at the substitution method. Let's look at the equations 2x plus y is equal to 10 and y is equal to 3x. Now the substitution method takes note that the solution to both equations will have the same y value and the same x value. So if here I find that y is equal to 3x, then this y should also be equal to 3x, which means I can substitute in that 3x in for y into this first equation. What that gives me is 2x plus 3x is equal to 10. I then combine my like terms. 5x is equal to 10. Divide by 5 to solve for x, and x is equal to 2. Now I plug in that 2 into the second equation for x, and I find that y is equal to 3 times 2, or y is equal to 6. So I have the solution here to 6. So this is called the substitution method. I substitute in what one of the variables equals in terms of the other. So I plugged in 3x for y into the other equation. I solve for that other variable, x, and then once I find x, I still need to find out what my y was equal to. So I plug in that x value into this y equals 3x, or I could have also plugged it into 2x plus y is equal to 10, just so long as I'm plugging it into one of these original equations that still has the y variable in it, so that I can find y. Now we can go ahead and check this solution to 6 for both of these equations. Checking this first equation, again 2 plugging in for x, and then plus 6 is equal to 10, and then here 6 is equal to 3 times 2. So here in both cases, 4 plus 6 is equal to 10, that is a solution, and 6 is equal to 6, again, another solution. So 2, 6 is indeed the solution to our system of equations. Let's take a look at two more equations. Take a look at 3x minus 2y is equal to 2, and x plus 4y is equal to 3. Now the trick with the substitution method is to find a variable in one of the equations that has no coefficient, or a coefficient of 1. Right? This is our variable we want to isolate. Okay, we first isolate this variable without its coefficient by subtracting the other terms from both sides. So minus 4y from both sides, and I get x is equal to negative 4y plus 3. The reason I do this is now I can clearly see what x is equal to in terms of y, so that I can plug in this negative 4y plus 3 into x in my first equation. So again, that is the key to the substitution method. Isolate one of the variables first, and then plug it into the other equation. So we have 3 now times negative 4y plus 3 minus 2y is equal to 2. I distribute that 3, negative 12y plus 9 minus 2y is equal to 2. I can combine my like terms. Negative 14y plus 9 is equal to 2. Then I can subtract 9 from both sides. I'm going to move it over here. I have negative 14y is equal to a negative 7. Divide both sides by negative 14. And I have y is equal to a positive 1/2. So now I still need to take this solution, y equals 1/2, and plug it back into one of the original equations to solve for x. Let's go ahead and plug it into this first equation. I have 3x minus 2 times 1/2 is equal to 2, or 3x minus 1 is equal to 2. I'll add 1 to both sides, so I have 3x is equal to 3, divide both sides by 3, and I find that x is equal to 1. So my solution in this case, I'm going to write as an ordered pair, 1, 1/2. And that is the solution to this system of equations. Let's try one more. Let's take x plus y is equal to 2, and 2x plus 2y is equal to 4. Alright, again we want to find a variable to isolate first. In this case we can either choose to isolate x or y. Just because it'll look more familiar, let's go ahead and isolate y. We'll subtract x from both sides, and we have y is equal to negative x plus 2. Now we can plug this in to this second equation. I have now 2x plus 2 times negative x plus 2 is equal to 4. I distribute the 2, so I have 2x minus 2x plus 4 equals 4. Combine my like terms, and 2x minus 2x cancels each other out, and I'm just left with 4 equals 4. Now, when my variables cancel out and I'm left with something true, that means I have infinitely many solutions. Okay, that basically means that these two equations, if I were to graph them, overlap each other. They're the same line. So in this case, any solution that works for one equation will also work for the other equation because I got something true. Now if I got something that wasn't true, like 2 equals 4, this would tell me that these two equations will never intersect, and in that case I have no solutions, or just an example where I have two parallel lines. So again, if I get something true, I have infinitely many solutions. Something not true, right, it corresponds to parallel lines, and I have no solution. We'll take a look at an example of no solution when we get to the elimination method, which is our next method of solving a system of linear equations. So let's look at these two equations. I have 2x plus y is equal to 1, and 3x minus y is equal to 9. Now what the elimination method does is it takes notice that when I add something to both sides of an equal sign, I have to add the same thing to both sides. Now what I see here is that 3x minus y is the same thing as 9. So if I were to add 3x minus y to the left side of this equation, I can add 9 to the right side of this equation, and I will be adding the same thing to both sides of the equal sign. So let's go ahead and do that. What this gives me is 5x, y minus y cancels out, and then I have 1 plus 9 10. The idea behind the elimination method is to make sure that when I add this left side of the equation, that I will have at least one variable that will cancel out. So in this case, the y's were already set up to cancel out because they had opposite coefficients, a positive one and a negative one. So that just left me with an equation with just x that I can now solve for x. Divide both sides by 5, and I have x is equal to 2. Now, just as with the substitution method, once I find the answer for one variable, I have to plug it into an equation to find the other variable. So I have 3 times 2 minus y is equal to 9. So I have 6 minus y equals 9. Subtract 6 from both sides. I have negative y equals 3. Divide by a negative 1, and y equals a negative 3. So my solution in this case, 2, negative 3. And this is the solution to both equations. Next, let's do 2y is equal to negative 6 minus 5x, and 2x is equal to negative 5y plus 6. The first thing I want to do then to work with the elimination method is to write both of these in a standard form, where I have x and y's on the left and a number on the right. So I'm going to do that. I'll add 5x to both sides here, and I get 5x plus 2y is equal to negative 6. Here I will add 5y to both sides, and I have 2x plus 5y is equal to 6. So now these two equations, right, they're the same as the original equations, they're now just in the form that I want to use. So now that I have them in a standard form, my next challenge is to make sure that when I add these two together, I have a variable that will cancel out. So now if I take a look here, I don't have any variables that will cancel each other out just yet. What I can do then is to pick a variable that I want to cancel out and change their coefficients with some multiplication so that they will cancel out. Let's go ahead and choose to cancel out our x's. Right? If I want to cancel out our x's, they currently have a coefficient of 5 and 2. I need one to be positive and one to be negative so that they will cancel out. Also, if I find the least common multiple of 5 and 2, I can change their coefficients to that so that they will cancel out. Basically, what I mean is, if I change this 5x to a 10x, and this 2x to a negative 10x, that when I add these two together, they will cancel out. I can change this by multiplying both sides of this equation by 2. If I multiply both sides of the equation by 2, I get 10x plus 4y is equal to a negative 12. Over here, I'm going to multiply both sides of this equation by a negative 5. I chose a negative 5 because I want my coefficients to have that opposite sign. So I have negative 10x minus 25y is equal to negative 30. Now when I go to add these two equations together, that x term will cancel out. So let's add this second equation to the first. I have negative 10x minus 25y is equal to negative 30. I'm going to add these two together. So my x's cancel out. I have a negative 21y is equal to a negative 42. I divide both sides by a negative 21. And I have y is equal to a positive 2. Now that I have y, I can plug it back into one of the original equations, either at this stage when I had changed the coefficients, or at this stage in red before I had changed the coefficients. So it doesn't matter which one I try. Let's go ahead and take, say, this here, 2x plus 5y equals 6. So 2x plus 5 times 2 is equal to 6, and then solve for x. So 2x plus 10 equals 6. Subtract 10 from both sides. 2x equals a negative 4. Divide by 2, and I have x is equal to a negative 2. So my solution then, negative 2, 2. So what we saw then is, for the elimination method, we want them in a standard form, variables on the left, numbers on the right, and then we may need to multiply the equations so that their coefficients are opposites, so that when I add them together, they will cancel out. And from there, it's the same procedure. I add them together, find one variable, plug that into an equation to find the other variable. Next, let's try 3x plus 3y is equal to 6, and x plus y is equal to 1. Now again, we want to use the elimination method. We already have x's on the same side, so x's and y's on the left and numbers on the right. So now we just need to pick which variable to cancel. Let's go ahead and cancel our x's, which means I need my coefficients to be opposites. I can easily do this by making this x here into a negative 3x by multiplying both sides by negative 3. So multiply by negative 3 on both sides. I have negative 3x minus 3y is equal to negative 3. Now I'm going to add these two together. So here's my negative 3x minus 3y is equal to negative 3. I go and add them together. 3x minus 3x is 0. 3y minus 3y is 0. I have nothing on the left side now. And 6 minus 3 is 3. And I'm left with 0 is equal to 3. Well, that is not true. What this means then is these two original equations are parallel to each other. They never intersect. Right? And I got something false here, which meant that I have no solutions to this system of equations. And just a reminder, right, if I get something false, that's parallel lines, right, and I have no solution. Whereas if I get something true, say like 2 equals 2, that is where the two equations form one line, and I have infinitely many solutions. Now we have one last thing to go over, and that is linear inequalities. Let's first take a look at some linear inequalities. Say, for example, if I had y equals x, an inequality is, instead of using an equal sign, I'm either going to be using less than or greater than, or less than or equal to, or greater than or equal to, using these symbols instead of the equal sign. So let's take a look at what that does to graphing the equation. So let's say instead now I'm using less than instead of my equal sign. So less than, y is less than x. If I go to graph that, I'm going to find the points the same way I always do. Right? There's no y-intercept, so I have the point 0, 0 here. And then I look at my slope of 1, I go up 1 to the right 1 to find my next point. Now when I have the less than symbol, right, it means y is less than x, so it's not actually going to be x, which means it won't actually be, right, the line that is formed by combining those two dots. Right? So to show that this line is not actually a solution, I use a dotted line instead of a solid line to show that it's not actually one of the solutions. Then I also take a look here, y is less than x, which means if I have a value of y that is less than x, that will be a solution. So if I'm down here below this line, right, where y is 1 and x is 4, here this point y is less than x, so this point is a solution to this equation. What we find then is that everything below this line is a solution to our equation. So when graphing y is less than x, I find the points the same as I always do. And just now, if there is no equal to, right, I have to use a dotted line, and then I have to shade either below or above the line to show where those solutions actually lie. There's a little trick to this. If I take a look at this here, I can split this up. Right? These top two, right, do not have the or equal to symbol, so here I'm always going to have a dotted line. For these two down here with the equal sign, I'm going to have a solid line, and a solid line will show that that is a solution. So for example, y is less than or equal to x, right? The only change here would be that this line becomes solid. Another trick, right, is if I write this in slope-intercept form, that is with the y by itself and on the left side of the inequality, then these symbols can also show me where I can shade. So for less than or equal to, I'm always going to shade below the line, and for greater than or equal to, I'm always going to shade above the line. Again, this is only true, right down here, these are only true if I'm using, right, my slope-intercept form, y equals mx plus b. Again, either using my less than or equal to or greater than or equal to, less than or greater than symbols. Let's go ahead and graph something else using this. Let's graph 2x plus y is greater than or equal to 2. Now I want to write this in slope-intercept form so that I can use all of my tricks. I'm going to subtract 2x from both sides, and I have y is greater than or equal to a negative 2x plus 2. So this is what I will be graphing. Looking at this symbol, it has the or equal to option here, which means I have a solid line, and it's in slope-intercept form with a greater than symbol, which means I'll be shading above the line. So let's go ahead and find that line. My first point is at 0, 2, my y-intercept, and then my slope is in negative 2, which means I go down 2 and to the right 1 to find my next point. I'm using a solid line to connect them, so I can connect these with a solid line. Right, and then I will be shading above the line. So I go up here above the line and shade everywhere that is above that line. So this then is the graph of y is greater than or equal to negative 2x plus 2. Next we're going to take a look at using graphing to solve two linear inequalities, but our focus, what I will be stressing on homeworks, quizzes, and tests is the idea of graphing just one linear inequality. We'll look at two relatively simple examples. Let's take a look at y is less than 2 and x is greater than or equal to negative 1. So what I'm going to do is graph both of these onto this coordinate system and then shade in the appropriate areas. So for this first one, y is less than 2. Right? This is a horizontal line at y equals 2. However, I do not have that or equal to option, so it's going to be a dotted line, right, where y is equal to 2. So this is the line, and then where I shade, again it's in slope-intercept form, I'm going to be shading below the line. I'll be shading right in this direction. I'm not going to shade it all yet because I haven't graphed my other equation yet. Now graphing x is greater than or equal to negative 1. This is a vertical line at negative 1, okay, and I do have the or equal to option, which means I can graph a solid line, right, at x equals negative 1. Now, as far as shading above or below, in this case there is no above or below, there's a left and a right. So let's take a look at that. Alright, x is bigger than or equal to, alright, larger than or equal to -1. So numbers that are larger or greater than -1 are over here to the right of this line. So what we find then is the place where both of these want to shade, is where both of their arrows are pointing, is this area right here, below the red line and to the right of the yellow line. So we can shade in that area, right, and that is the solution to both of these linear inequalities. So now when solving systems of linear equations, you now have 3 methods to choose from to solve those linear equations. Also, don't forget to practice some of the linear inequalities. That will do it for chapter 4, and I will see you next week for chapter 5.